Today we'll be talking about functional groups in organic chemistry. The most important element in organic chemistry is carbon. It has 4 valence electrons, which means it has 4 bonds. With this information, we can go over the 4 different ways a molecule is represented. We have molecular formula, structural formula, condensed structural formula, and skeletal formula. Naming functional groups with the IUPAC. Let's look at the first table. When naming organic compounds, we need to look at the longest carbon chain. Depending on how many carbons there are, this will be the prefix. For example, 1 carbon is meth, 2 carbons is eth, and 3 carbons is prop, and so on. Depending on what functional group you are looking at, this will be the suffix. For example, alkanes end with ane, alkenes ends with ene. If we had 3 carbons and it was an alkane, it would be propane. 4 carbons, it would be butane, and so on. We'll go over more of this when we talk about each functional group. I've listed the rules from the IUPAC. I would like you all to take note of these as they are really important. To remember these rules, you will see further on in the lesson how this all comes into play with naming molecules and their functional groups. Alkanes are hydrocarbons, and what this means is they are only composed of carbons and hydrogen atoms. They are saturated, which means they only have single carbon-to-carbon bonds. These bonds are called sigma bonds, and they have direct overlapping of orbitals. The single bonds in alkanes are the result of orbital sp3 hybridization. This is where the p orbitals in carbons overlap the s orbitals in the hydrogen atoms. You can see this on the diagram on the screen now. Alkanes form a homogeneous series. This means they have a general formula. In this diagram, you can see we have the longest carbon chain with 4 carbons, and we have 1 branch attached to the second carbon. The branch only has 1 carbon in it, which we know is the methyl group, so it is an alkane called 2-methyl-butane. You can also get cyclic alkanes. The diagram shows you 6 carbons in a ring formation, so this alkane is named cyclohexane. I want to run through a few key facts about alkanes. Alkanes are colourless, alkanes are insoluble in water, and alkanes are unreactive. The melting and boiling point of alkanes are shorter in the low chains, but this increases when the number of carbons increase. Please see extra physical properties and chemical properties on the screen now. Alkenes are hydrocarbons, the same as alkanes. However, it is unsaturated, which means it has at least 1 carbon-to-carbon double bond. This carbon double bond is highly reactive compared to an alkane. This is because of the double bonds have high electron density. When naming alkenes, we need to identify the longest carbon chain. There are 4 carbons, so we know it is butene. You can notice the double bond is attached to the second carbon atom. This alkene is but2-ene. The next alkene has the same amount of carbons and hydrogens. The only difference is the double bond is attached to carbon number 1. Therefore, the name will be but1-ene. This is what we call an alkene isomer. Alkenes are similar to alkanes as they are nonpolar with low boiling points that increase with molecular mass. Alkenes with 2 and up to 4 carbons in a chain are gases at room temperature. When there are 4 or more, they become a liquid state. Alkenes can be oxidized and polymerized. Like alkanes, the alkenes undergo combustion. However, alkenes are less likely to combust completely, so they tend to burn in air with a smoky flame due to incomplete combustion. Please see more physical and chemical properties on the screen now. Alkenes have additional reactions. This is where you take 2 reactants to make 1 product. The reason alkenes can do this and alkanes cannot is because of the carbon-to-carbon double bond. Catalysts are needed in these additional reactions. The first example is hydrogenation. We have the first reactant, propene, and the second reactant, hydrogen. To make this product, propane, what happens is the reaction is the double bond breaks and opens and the 2 hydrogens get added to the carbon. The second example is halogenation. This is where the alkene and a halogen are used as the reactants. It is the same process as the first example. The alkene used is ethene. This will react with chlorine and the product produced will be dichloroethane. Sigma and pi bonds. Sigma bonds are the first bond carbon makes with any other atom. It is made from hybridized orbitals. The sigma bond is stronger than the pi bond as the overlap is greater and the orbitals are facing each other. Pi bonds are the second or third bond made with any other atom. This is made from the leftover p orbitals overlapping each other. These orbitals are parallel. This makes the molecule more rigid and pulls a sigma bond closer together. It takes less energy to break a pi bond. Please see the diagram below to look at where the orbitals are situated and how the bonds are made. Alcohols can be recognized when a hydrogen atom of an aliphatic carbon chain is replaced with a hydroxyl group. The OH is what we call the functional group in alcohol molecule. When naming alcohols, as usual, we need to find the longest carbon chain. We can see 4 carbons, so the prefix will be butane. This is because we have a straight carbon chain with only single bonds like alkanes. Next, we find the functional group OH and see what carbon it is attached to. This is attached to carbon 1. The name of this alcohol is butane 1-ol. I have also given diagrams of 1-pentane 2-ol and 2-methyl pentane 2-ol to help you see the IUPAC system when naming. The reason why I chose these 3 specific molecules is that alcohol fall into different classes depending on where the OH is situated on the carbon chain. The classes are called primary, secondary, and tertiary alcohols. Primary alcohols, the carbon is attached to the alcohol group, will only be attached to one other alkyl group. Secondary alcohols, the carbon which is attached to the alcohol group is joined directly to 2 alkyl groups. This can either be the same or different. Tertiary alcohols, the carbon is directly attached to 3 alkyl groups, which may be any combination of the same or different. Alcohols have higher boiling points compared to other hydrocarbons. Alcohols are soluble in water, and alcohols also have a sweet odor. In the presence of oxidizing agents, alcohols can produce aldehydes and ketones. In dehydration of alcohols produces alkenes. Please see the slide for more physical and chemical properties of alcohols. Aldehyde and ketones are very similar molecules in that they both have a double bonded oxygen attached to a carbon. What separates them is where the oxygen is in the molecule, and that will determine whether it's an aldehyde or a ketone. You can see 2 examples. The first molecule is an aldehyde as the functional group is attached to the N carbon. This is called ethanol. The second example is a ketone as the functional group is attached to the second carbon. This is called butane-2-one. Aldehyde and ketones are carbohydrates, also known as the carbonyl group. We are going to have a look at well-known aldehyde and ketones and go through their differences. Glucose and fructose. You can see they both have the same chemical formula, but the placement of the double bonded oxygen is different. Aldehydes are found in volatile compounds, are more reactive, easy to oxidize due to the hydrogen atom, and the Benedict's observation is an identification test to test whether aldehyde or ketones are present. If an aldehyde is present, a dark red precipitate will show. In ketones, they are found in sugars, they're less reactive. Oxidation cannot happen without breaking the carbon chain, and with the Benedict's observation, there is no change to the blue colour. It remains as there are no aldehydes present. Carboxylic acids is an organic acid that contains a carboxyl group attached to an alkyl group. They are one of the easiest to identify because of the COOH at the end of the molecule. Because of the double bonded oxygen, it can only ever be at the end. There are 2 examples showing naming. We are going to be looking at the second example. There are 5 carbon atoms and they have a methyl branch coming off carbon number 3. So the name is 3-methyl pentanoic acid. Many carboxylic acids are colourless liquids. They have disagreeable odours and they have high boiling points. Solubility decreases as the carbon chain length increases. There are more physical properties listed there, but now I really want to talk about reactions with carboxylic acids and alcohols. We are looking at pentanoic acid and ethanol, and this is going to create ethyl pentanoate. When a carboxylic acid is treated with an alcohol and an acid catalyst, normally a concentrated sulfuric acid, an ester is formed. This reaction is called Fischer esterification, which brings us to our next functional group, esters. Esters are formed by a condensation reaction between an alcohol known as glycerol and a carboxylic acid. The reaction is known as esterification. In a condensation reaction, two molecules join to produce a larger molecule whilst eliminating a small molecule, H2O. Esters are fats. They're saturated, known as trans fats, and unsaturated, known as cis fats. To name an ester, you change the name of the parent alcohol to end in YL and change the name of the parent acid to end in OATE. Alcohol names go at the front and the acid name goes at the back. The example you can see is methanol as an alcohol and ethanoic acid as a carboxylic acid. You can see that the molecule loses two hydrogens and an oxygen to become an ester. The name of this ester is methyl ethanoate. Some key physical properties. Distinctive smells, good and bad. Some esters are very soluble in water, but the solubility falls with the chain length. Esters have lower boiling points to their isometric carboxylic acid counterparts. Natural esters are found in plants and animal sources. Some uses for esters, you can use them in perfumes, food additives, glues, and also chemicals used to soften plastics. Amines are derived from ammonia. The functional group is a nitrogen atom with a lone pair of electrons. When naming an amine, it's the same as all the other functional groups. There are 7 carbons. The functional group is attached to carbon number 2, so the name will be heptane 2-amine. Amines also have primary, secondary, and tertiary groups. You can see in the example, each group you are losing a hydrogen atom and replacing it with either an alkyl or an aryl group until they are all replaced. Some physical and chemical properties of amines. Primary amines with 2 to 4 carbons are a liquid state at room temperature, with the higher ones are a solid state. Lower aliphatic amines are soluble in water, while higher amines are insoluble in water. And primary amines have a higher boiling point. I've also named some uses of amines on this slide. Amines are derived from carboxylic acids in the amine group. You can see there are 2 carbons, so this will be ethamine. The example you can see shows the condensation reaction of 2 functional groups to create an amide. Please have a look at the slides for some key physical and chemical properties of the amide group. On this slide, we are looking at structural isomers and stereoisomerism. Structural isomers are any 2 or more chemical compounds having the same molecular formula but have different structural formulas. In stereoisomerism, the atoms making up the isomers are joined up in the same order but still manage to have a different spatial arrangement. There are 2 forms of stereoisomerism, diastereoisomerism and optical isomerism. The main difference is diastereomerism cannot be a mirror image, while optical isomers can be mirror images. Please look at the slide for more information on these. The identification and characterization of the structures of an unknown substance are an important part of organic chemistry. I have some results from an identification test that we have done on different functional groups. As you can see, the different compounds behave differently depending on what the reactant is used in these experiments. Each functional group has a particular set of chemical properties that allow it to be identified. Some of these properties can be demonstrated by observing solubility behavior, chemical reactions which are accompanied by a color change or precipitate formation, or other visible effects. Please see all the results on the table on the slide. We have gone through most of the functional groups in organic chemistry. Almost all molecules inside any living thing can be classified as either carbohydrate, lipid, proteins, and nucleic acids. It is important to understand the reactions of simple organic molecules. Their carbon skeletons are held together by covalent bonds. They form cells of an organism and perform chemical reactions to facilitate life. One of the reactions is condensation reaction in carbohydrates. This is where H2O splits out and two glucose molecules are linked together by a glycosidic bond to form maltose, which is a disaccharide. Lipids have esterification. Proteins have peptide bonds formed by biochemical reactions that extracts the H2 molecule. This should cover most things in organic chemistry. Please let me know if you have any questions, and thank you so much for listening to my presentation.